problem now. And so I wrote it up on my paper here. I'm going to do that in a minute. And actually, if you're writing this down, maybe I'll pause. I'm going to put this into Desmos and just take a look at the graph for a second, see if that helps me say anything about it. So let's do that. Yeah, so I decided to go graphing calculator times x plus 2, close parentheses, and I'm just going to do a standard graph. And there it is, right? So why does it look like that? Well, what degree is this equation? If you multiplied it out, it would be degree 4, right? Okay. And so this is a possibility of what a 4th degree equation might look like. We might not have studied those as much. Looks kind of like a W to me. And now the tangent line, I guess if I wanted to graph the tangent line at that point, first of all, let me point out that if I hit second calculate, well, that's trace. If I hit second trace and if I choose the value x equals 1, it'll compute f of 1 for me. And sure enough, f of 1 is negative 3. Right? So f of 1 is negative 3. That's that point right there. And I want to find an equation of this tangent line. So, you guys know, I think, what form have we used for the equation of a line quite often? We've used slope-intercept form, but we've also used what? Point-slope form, because I have a point, right? There's my point. And I should be able to get the slope. How am I going to get the slope? Find the derivative, right? So I know that my equation, whatever it is going to be of the form y minus y1 is m times x minus x1. And actually, I can fill most of that in already, right? What can I fill in? Well, where it says y minus y1, what could I write? Y plus 3, because we have negative 3 for y1, is equal to, what else can I fill in? Yeah, I guess we don't know m, but we're going to get x minus 1 here, right? Now, as far as the slope, okay, I can tell you what it is. It's going to be from f prime. F prime of what, though? Of 1. Because when you find the equation of the tangent line, you have to plug in that x value to get the slope into the derivative. My problem is I don't know the derivative yet. So I'm going to need to compute f prime of x. I'm going to have to compute that. All right? So how do you compute it? Well, if I had given this to you on exam 1, which I don't think would have been very nice, okay, what'd I give you?
I gave you 1 over x minus 2.
Oh. 1 over x minus 2. So how did you do that?
That's the thing.
Oh, I didn't give it to you. Oh, I know what happened, right? If I gave you 1 over x minus 2, you had to do it the long way.
Yeah.
Okay, well that's good. Then I got to test the long way. Can you imagine doing this one the long way?
No.
Me neither. X plus h cubed minus 3x plus h, x plus, oh yeah. Ooh, okay. So yeah, maybe you got kind of this far on the problem, but maybe you were stuck with what the derivative was. Well, I guess we're in familiar territory.
I think that was one of the ones that was planning on redoing, but
Oh man, okay.
and it was like 18 points.
Well, it depends who it was. Some of you it's 58. Just depended on whose exam it was. All right. Anyways, so f prime of x. So, but if you got this far, I mean, you knew mostly everything. Now the fact of the matter is, can I find this derivative? Okay. So one way to do it would be to take that x plus 2 and distribute it. In other words, x times all this, 2 times all this, and you'll get that 4th degree polynomial, whatever it is, then take the derivative. But that takes time. It turns out that the fast way to do this problem, okay, is with what's called the product rule. So if I go back to the product rule, I wrote it here, okay, the derivative of two functions, f times g, will be the following. F prime of x times g of x plus f of x times g prime of x. Okay? And I'll show you why that's true here. I think this is actually an interesting little thing. So let me write it down and give you a little how to do this. Okay? So let's do this. Let's suppose we have, we'll come back to the equation of the tangent line problem. What?
That looks familiar.
Yeah?
Uh-huh.
So
To something from Prig.
suppose I have, I'm going to call big F of x the function little f of x, little g of x, multiplied together. And what I want to learn here is I want to learn how to take a derivative of a product. And I don't know how. So just like you had to on your exam, when I want f prime of x, I'll use the definition. Limit as h goes to 0 of big F of x plus h, right, minus big F of x all over h, right? That's what it equals. And now I'll fill some things in. And just like I did with you guys, I'm going to use a big fraction here. So the denominator is h. Now, please do me a favor when you're doing this. See where it says big F of x? What are we going to replace that with? Well, little f, little g, right? That's what big F of x is. But let's put it way over here on the right. Little f of x, little g of x is what we're going to be subtracting. Okay? Now, over on this side, way on the left, what am I about to write?
Little f of x plus h.
Good.
Little g of x plus h.
That's right, because that's what big F of x plus h is. But you notice I skipped some space here. And that's because I'm about to do a trick. And who thought of this trick? I'm blown away by this. Like, who would have thought of doing this? But someone did. We can subtract the following. Little f of x plus h times little g of x. And that's allowed as long as we also add little f of x plus h, little g of x. Correct? Nothing wrong with doing that. But I guess the question is, why did I do that? Well, I'm about to use a property of limits here, which says that the limit of the sum is equal to the sum of the limits. And so I'm going to split this up basically. This huge fraction, I want to split up into two fractions. Both fractions will have what as their denominator? H. When you add fractions with the same denominator, you get the same denominator. Okay? And so what I get for the first fraction, I have little f of x plus h times little g of x plus h minus little f of x plus h times little g of x. Right? What's the second fraction going to be? Yes. F of x plus h g of x minus f of x g of x. Okay? And we're going to work on these fractions separately. In particular, I want to work on the second one right now. Any idea what I'm going to do with the second fraction? Well, I have a g of x here, and I have a g of x here. Do you know what I might do with that? Pull it out. Factor it out. Right? And if you factor it out, whether you put it out front or whether you put it out in the back, it's interesting what you get. because you have limit as h approaches 0. If I what is this? Yeah. In other words, I can replace this piece times g of x. You see that? Plus, so now what's the other piece? Well, let's see. Can we do the same kind of an approach here? Well, I guess we kind of can. What's the common factor we can take out? We could take out an f of x plus h, right? So if you do that, you now have the limit as h approaches 0 of f of x plus h, okay, times the limit as h approaches, here I'm using the fact that the limit of the product is the product of the limits, and what are you left with? G of x plus h minus g of x all over h, right? So what just happened? What is this big fraction when the limit as h goes to 0? What does that give you? G prime of x. And then this stuff here, what does this give you? That's f of x. Because as h goes to 0, f of x plus h is going to approach f of x. And so what we just did is we proved, if you want, or developed the product rule. There it is. If you have a product, from now on I don't need to do limit as h goes to 0 stuff. I can do it this way. F times g prime of x plus f prime of x times g of x. Okay? Now if you look back at the slides that I have talking about this stuff, you'll notice when I did problem 63, I wrote the product rule another way. I used u's and v's. And whenever you see me using the letters u and v in this class, I want you to understand u and v are functions of x. Okay? I won't write u parentheses x very often because I'm trying to cut down on the amount that you have to write. Okay? But basically, another way to write the product rule is u prime v plus uv prime. Okay? So for example, when we go to do this problem, okay, here, let me write out the rule and show you how I would use it. So over on the side, the derivative d dx of uv is equal to u prime v plus uv prime. You take the derivative of the pieces separately. So watch how this works. Here, let's call this u, and here, let's call this v. Okay? So when we go to do f prime of x here, we can just do u prime v, first of all. So what would be u prime if u of x is this function here? So u prime would be what? What's the derivative of x cubed minus 3x plus 1? 3x squared minus 3, and then plus 0, right? Because the derivative of a constant is 0. Are you guys able to do that? Good. So that's the u prime. And then let's write down v again, which is just x plus 2. Okay. Plus, so I need a plus sign. And now I need what? u v prime. So the u here would be, well, x cubed minus 3x plus 1. There goes my screen. And then what's the v? What's the derivative of x plus 2? It would just be 1, right? Because it's 1 plus 0. So now you have this mess. And if we want to finish the problem, what's the last step? I take that and do what with it? What's that? Not necessary, not for what I'm doing, right? Because if you look at what the goal is, right? We want the slope of the tangent line. See, if I multiplied everything out, you're right. I could, and I would have a simplified expression for the derivative. But I think I'm at the point now where I ought to be able to compute f prime of 1. How? Just take this big ugly function and do what with it? Plug in a 1 everywhere there's an x, right? So I'm going to save myself the multiplying and just go f prime of 1 at this point. And 1's a nice number. I mean, look at what you get. You get 3 minus 3 times whatever, because once you get 3 minus 3, that's 0. Plus, and over here, what do I get? I get 1 minus 3 plus 1. So what's 1 minus 3 plus 1? Times 1. So I'm just getting negative 1, is that right? Negative 1. So now we can finish the problem. We know that the derivative is negative 1. So my answer, one equation would be y plus 3 is negative x minus 1. Right? Could we put that in slope-intercept form if I wanted?
Yeah.
Sure, let's do it. Y plus 3 is negative x plus 1. So y is equal to what? Negative x minus 2, okay. And let me go ahead and graph that on my picture so we can take a look at the graph and see that that works as the tangent line. So if I go back to the picture, there's the function. Let's graph y equals, on the second line, negative x minus 2. Let me graph that. And is it tangent right where I want? Right here, let me do this. I'm going to zoom in a little bit. And before I zoom in, I'm going to move the cursor down so I'm zooming in really close to that spot. I want to see it. Enter. And you can see, right? Here's the point 1, negative 3. Right here. Here, let me do that again. Second, calculate a value, x equals 1. Right there, y is negative 3. You guys see that? So there's your point of tangency. We found the equation of the tangent line, and that's the kind of thing you had to do, well, even in the last chapter as well. Okay? Of rewriting the function, right? So when I have, let me write down f of t, here, f of t is the cosine of t divided by t, right? But if I want to use the product rule, I have to rewrite it. So how am I going to write it? Instead of writing divided by t, you could instead write t to the negative first power, see that? Times cosine of t. Does it make sense? So here's u, and here's v. Ashton, you with me? Okay, so I have u and v there. And now when we go to compute f prime, right? F prime of t, I know what I need to do. The derivative is going to be u prime v plus u v prime. Oh, actually, this gets at, if you wanted to use a shortcut for that one on the test, I guess we could have written it as x plus 2 to the negative first power, right? But I wasn't intending you guys to be able to do that yet, okay? But if you thought of it, great. But if you write this, do we know how to find the derivative of t to the negative first power? Yeah? How? Or what would it be? So remember that power. What if it said t to the third power? Would you guys know what to do? What would you write? 3t squared. Bing, bing, right? So I guess the question is, does Bing Bing work when you have negative numbers? Well, that answer is yes, it does. Okay? And we actually didn't know that until the reading. I don't know if you guys saw this, but in the reading, one of the first things they get to is, hey guys, remember the power rule, Bing Bing? It works for negative numbers. And they show you why using the product rule. Okay? And quotient rule, which we'll do next. Jeff?
Oh, no, I was
Okay.
just fixing my hair.
So here I go. Let's practice, guys. What's the derivative of t to the negative first? Negative, because I bring that negative 1 down. So negative 1 times t to what power? What's the next Bing? It would be negative 2, right? Because you have to lower it 1. You have to subtract 1 from the exponent. So it's now negative 1 t to the negative 2. And then times v, so I need to write times cosine of t plus, and now how about uv prime? Well, let's see. U would be t to the negative 1, right? Times v prime. Do you guys know the derivative of the cosine function? It's negative sine. We did it on that group work using that identity that Mike was talking about, right? So look at that big mess. That is the derivative, okay? And let me explain a little bit of what your homework's going to be like this week. You're going to be doing a problem. They're going to say, find the derivative. You're going to do this. And then you're going to check with Bob, right? And he won't have that answer exactly because what's he going to do? He's going to simplify. So if we're going to simplify this, what kinds of things might we do? We might write, let's see. Well, maybe when I see that t to the negative 2, what am I going to do instead of writing it that way? We'll put it over t to the positive 2, right? So you have to get comfortable again with what negative exponents are. So yeah, this maybe we would write, maybe Bob would write negative cosine of t over t squared. And then what would we do here? Maybe you'd have plus, and then you might have negative sine of t over t, or something like that. Maybe Bob would put that. The other thing Bob might do is Bob might write this as one big fraction. So now if you want to write it as one big fraction, can you add these fractions? You only can if you multiply top and bottom by what? By t, so that you'll get a common denominator of t squared. Okay? And the other thing that they might do, see there's a negative in each of them? We could factor it out and just put a negative here. And now what would be left in the numerator? Cosine of t plus, because I took a negative out of each of them. No, it would be t times the sine of t. The t was multiplied by the sine of t. I wouldn't say t squared because that'd be inside the function now. So we would put the t out front. Okay? So maybe Bob would put this as the answer. But please understand that if you wrote this as the answer, that's also correct. That's the derivative. So I guess, do I want you to keep simplifying? Yes, because you'll learn an awful lot of algebra and trigonometry in your calc class as you try to get the answers. But if I said, find the slope of the tangent line, I'd probably use this very first form rather than trying to go through all of that. Does that make sense to you guys? Okay. So that's kind of where you're headed as far as the homework looks. And so now I want to talk about the quotient rule. The quotient rule is a little more complicated. If you have f of x over g of x and you try to compute the derivative, okay? Personally, I wouldn't write that down. I would write this down instead. This one's easier to remember. The derivative of high over ho. You have the high function on top, and the low function we'll call ho. High over ho. because then it's easier to remember. Here's the quotient rule. Ho d high minus high d ho over ho ho. Isn't that fantastic? Ho d high minus high d ho over ho ho. I'm going to show you how to use this, okay? Let's go back to the problem we were just doing. And let's do the problem over again using the quotient rule. I mean, we had a quotient, right? So, let's do this again with the quotient rule. And so I'll write the quotient rule over here. The derivative of high over ho is equal to ho d high minus high d ho. And by d, I mean derivative. All over ho ho. This is how I remember it. It's a lot easier than trying to remember where the F's and G's are for me. So here I go. We're going to compute f prime of t for the very same problem we just did. And so it's a fraction. And the very first thing we're going to write is we're going to write ho d high. Ho. So what am I going to write where it says ho? T. Okay. D high. What's the derivative of cosine of t? We know it's negative sine of t. So there's ho d high. Minus high. What would I write? Cosine t. D ho. So what's the derivative of t? It's 1, yeah. We're taking the derivative with respect to t, and so that's 1. So ho d high minus high d ho, all over what? T times t, which is t squared, yeah. So if we want to simplify this, we get t squared here. Do we get the same thing? I have negative t sine t minus cosine t. Is that the same thing we got before? You see it, right? That's pretty much, you take the negative out and reverse a couple things and you have the same exact thing. Okay? So quotient rule is a nice rule. Now, guys, I didn't derive it or prove it. It's done in your book. How do you do it? F of x plus h minus f of x all over h. Take the limit as h goes to 0. Go through some steps and you get it. Okay? I don't have any need for that. If you want to look it up in the book, that's cool. I just want you guys to be able to use it. Yeah, Calvin?
So, like, if I want to do this type and not like the upper type, could I just take a product and divide it by 1 and then just say use this rule instead, theoretically?
If you had a product and you say, I don't like the product rule,
I divide it by 1, is it still?
you can. You could, if you're careful enough. Now, you guys understand Calvin's question? He's saying, look, just like I didn't want to use the quotient rule, so I turned it into a product. He said, well, couldn't you take a product and turn it into a quotient? Yes, you could. Okay? I want you guys to understand one thing about derivatives. I'm giving you these rules, but until Friday, when we cover the chain rule, okay, we're kind of stuck. There's some things I really can't do yet. Now, this is last week, but this Friday, we cover the chain rule. Then we'll kind of be fully armed to find derivatives of just about anything. Right now, I have to be careful. So when doing the approach you applied, you might get stuck now. I would say wait a week and then try what your idea was. Okay? Rather than saying, why doesn't it work? Might be because you don't have the chain rule yet. Well, anyways, I think the one I wanted you guys to do next was cosecant. Yeah, let's, because actually, if you take a look at our calendar, since we had it up, notice what I'm supposed to cover next. Derivatives of trig functions. So we've already done sine and cosine. Derivative of cosine is negative sine. What's the derivative of sine? It's just regular cosine, right? So those are nice. But what if you have another trig function? So I mentioned cosecant. How would you find the derivative of the cosecant of x? Let's do it. Let's find the derivative of the cosecant of x. Well, first of all, you have to know what I mean by the cosecant. We're going to rewrite it. How am I going to write it, guys? It's 1 over the sine. That's what it means. It's one of the reciprocals, right? So the cosecant of x is 1 over the sine of x. By the way, I can't remember if tangent is a homework problem. That might have been a quick check for Wednesday. How would you rewrite tangent function? Sine of x over cosine of x, and then you could use the quotient rule and you could find the derivative. But let's do cosecant. This is a good example. So let's see. If we want to find the derivative of cosecant, and I write it like this, now I'm in position to do ho d high minus hi d ho over ho ho. So let's try it. Ho d high. Well, what's ho? Sine of x. Make sure you write the x. Sometimes I see people like ignoring this argument. They just write, and that's a sin, so don't do that, guys. All right. So sine of x times d high. What's the derivative of 1? It's what? 0. Okay. Minus hi d ho. So we're going to write 1 times what? Cosine of x. All over ho ho. What will we write? We can write that as sine squared of x. That's right. So if you told me the derivative of cosecant is negative cosine x over sine of x times sine of x, or if you wrote sine squared x, either one, you'd be correct. That's right. But if you look in your book, inside front cover, do you guys know they give derivatives of all different kinds of functions there? I think so. Where's it at? No, it's not inside cover. Oh, wait, that's where they give all your old... So they give you a lot of nice formulas. That's not the derivatives, though. Where do they give the derivatives?
In the back.
In the back. Let's look at the back. Ah, there they are. So what's the derivative of cosecant x, they say? Look what they say. Negative cosecant x cotangent x. Now why? Well, first of all, notice for all the trig functions, they're trying to write them not as fractions, but just with other functions. So did we get it right? Can you see it? Negative, we have the negative. Now, they say cosecant x. What is that? That's 1 over the sine times what? Do you see the cotangent x? What's cotangent mean? Good, because it's the reciprocal of the tangent. So tangent is sine over cosine. So here, that cotangent is coming from cosine of x over sine of x. That's this piece. And then the 1 over sine x becomes cosecant. And so the derivative of cosecant of the cosecant of x is negative cosecant x cotangent x. Okay. And now we actually have the ability now to do all the trig functions. And so that's your quick checks that you're going to read for Wednesday, or one of the 2 sections I cover Wednesday is on that.
Don't you have to split cosine x into like 2 different cosine x over you have to split it, so it's cosine x over sine x. Yes,
So,
cosine x over sine.
yeah, I mean, I guess you're saying, how do I get from here to here, right?
Yeah.
So what I did at the end here is I kind of wrote it as negative 1 over sine x times cosine x over sine x. Notice this is a times sign, not a plus. How do you multiply fractions? Sine times sine is sine squared. So each one gets one of those.
I thought both had to have cosine.
Yeah, not when you multiply, right? So we're multiplying. Whereas that other problem, like up above, I was adding fractions, they had to have the same denominator, then you get it this way. It's funny how the adding fractions and multiplying fractions come up again, even in calculus. You see very different things. All right. Oh yeah, rate of change. Higher order derivatives. Now we talked about higher order derivatives already, like the second derivative. But so again, you look at what I'm doing on Wednesday. I'm going to be talking about the derivatives of the trig functions. I'm also going to be talking about the derivatives as rates of change. We already know this quite a bit, right? What do we know the derivative is? We had AROC and... So the derivative gives you an instantaneous rate of change, as opposed to just the slope of a secant line as an average rate of change, right? And I thought there was a really nice example in the reading for today, so I want to go to it. Here, rates of change. See that? So here we go. The derivative provides information about IROC. The next example illustrates this concept. I thought this was really good. So it says P of t equals 400. So the reason they use P instead of F is because they're talking about a population of cells. And the reason they use T instead of X, usually little t stands for time, right? It says here this time is measured in hours. It says a culture of cells. So you get a throat culture, right? So what happens? Well, they swab and they put it in a little petri dish and then they wait. And the thing grows, right? How long do they have to wait? Well, it depends on your culture and your strep test, whatever you're doing. But anyways, do you know anything about the graph of this function, you guys? Without the calculator. I claim you should know something about it from test 1. Yeah, go ahead,
I
Calvin.
say it's just going to be like the same graph, but only 3 arc higher.
Why?
Just adding 3.
Adding 3. I guess I'm trying to understand what you're saying.
No, never mind.
Never. So when you look at this, they call this blue line the steady state. You guys see that? What's going to happen as t goes to infinity? We're going to move on, and eventually this guy here is going to move until we're really close to 400. That's an asymptote. Right? Now what we don't know is how many hours does it take. And we also don't know part C. When is the instantaneous growth rate the greatest? I guess what we just answered is part C. What is the steady state population? So that's what you were able to do before today. But what this example is talking about is your initial growth rate and your maximum growth rate. What are those going to be? Well, you need to compute the derivative, right? So let's do it. Let's compute the derivative of the function. I guess I need a new sheet of paper. And I need to write down the function. So let's see. We have P of t is 400 times, and we have t squared plus 1 over t squared plus 4. So there's P of t. And now I need to compute the derivative, right? So let's have you guys try using the quotient rule. Remember, when you go to do P prime of t, one of the reasons they took that 400 and put it out front is because I know I can ignore a constant out front, right? This is just going to be 400 times d dt, the derivative with respect to t, of t squared plus 1 over t squared plus 4, right? And so I can write that this is 400 times, and what rule do you think we're going to use here, guys? To find the derivative of this mess? What? Yeah, the Hody-High, the quotient rule. All right. Let me pause and let you guys try it, and we'll see what happens with that. All right, let's see if I can do this. Ho d high. Ho would be t squared plus 4. Where it says d high, right? Here, let me write down the rule so I don't forget. It's ho d high minus high d ho over ho ho. All right, so what am I going to write? Ho d high is t squared plus 4 times what? 2t. Minus high d ho would be t squared plus 1 times 2t. Over ho ho, you could write t squared plus 4 quantity squared, if you want. Right. And I don't think there's any need to multiply that out, t squared plus 4 times t squared plus 4. I would leave it like this. There probably is some need to simplify the numerator. If we're going to use this, it'd be nice to. So let's see. Let me work that out, the numerator, a little bit. Guys, stop me if you have questions, okay? So we have 2t cubed, right? Plus 8t. But then I get minus 2t cubed, right? And then I get what? Minus 2t, because we have to distribute the negative. And so I'm going to get 400 times, how about 6t, not 60, 6t over t squared plus 4 quantity squared. So that's what I'm getting for a derivative.
Why would we take the derivative of 400?
Because, kind of like this, let me go back to an example you guys had earlier. If I gave you y is 15x squared, and I said find the derivative, what would be y prime? You would just do 15 times 2x, right? 30x. But it's funny, I know you learned that rule, but then this is kind of a different context because the 400 seem, what am I doing with it? Well, I'm ignoring it, basically. So the derivative of a constant times the mess, you just ignore the constant and bring it down. Okay? So yeah, I mean, maybe at the end, maybe we would write p prime of t is 400 times 6 would be 2400t over t squared plus 4 squared, or something like that. That might be what we read, right? Anyways, back to the book. They graph p prime of t in red. There it is. 2400t over t squared plus 4 squared. They say it looks like that in red. Okay. Do I believe that? I guess maybe I'll try something like, what is p prime of 1? 2400 over, this would be 1 plus 4 squared. So it's 2400 over, well, 5 squared, right? Which is what? 25. And so if I do 2400, sorry, you can't see. So if I do p prime of 1, and I plug in the 1, I get 2400 over 25. I think that's 96, right? Because 2500 over 25 would be 100. And so if you look at the picture, again, when I plug in a 1, I'm almost up to 100. I'm at 96. You guys see that? And actually, one interesting thing might be, what is the highest that the red ever gets? Maybe that's it. Right around there, 96. Because that's what they ask in Part A. They say, compute and graph the instantaneous growth rate. Okay, well, actually, we did that. We computed the derivative and graphed. Part B, at what time is the instantaneous growth rate the greatest? So here's the initial growth rate was 0. And then the growth rate starts increasing, right? And if I ask what's the maximum growth rate, the maximum growth rate would be where is this the highest, this red? I guess the maximum growth rate is right around here. They say it's a little past 1.15. Okay, so the highest the derivative ever gets is 97, they're saying. Approximately. We just figured out where it's 96, right at 1. You go a little bit past 1, and then the curve is really growing. So basically, after a little more than an hour, we have rapid cell division in our culture. But by the time we get to 8 or 10 hours, there's very little growth at that point. And that's why you get to this steady state. Well, why does that happen in a culture?
Not enough food.
You might run out of room. You might run out of food, right? There's the resources diminish, yeah. So it's kind of interesting how that works.
So are we just supposed to kind of guess?
Well, I'll show you what it said in the reading. I thought this was funny. Here, watch. Solution. Okay. So they do the derivative. They got the same thing we did, right? Part B. The growth rate has a maximum value where the curve is the steepest. Using a graph utility, so yes, guessing from the graph. And then check out this note. Note. Methods for determining exactly when the growth rate is the maximum are discussed in Chapter 4. So yes, so you kind of have to wait, although I thought I might do it today depending on time. Kind of depends what other questions you guys have. So we could show you kind of how to do that today if you want. What's that?
We had to guess the point on the test too.
You had to guess one on the test? Okay. So this is 47. I'm supposed to find the derivative of this function g of x. And what I would advise here, if I had this problem, I would begin by simplifying it. Okay? So right away, what do you think I'm going to do? Yep, multiply that x, distribute. So I have g of x equals 3x minus x squared over 2x squared, right? And I'm still going to simplify because that can be written as two separate fractions, right? G of x is 3x over 2x squared minus x squared over 2x squared. And that makes it even nicer because now what you have is you have g of x equals, well, what about the second fraction? The x squareds cancel and you just get minus 1/2, right? Because those x squareds are going to cancel. The first fraction, I claim, is 3/2, and let's write it as x to the -1 power. Wow. I didn't use any product rule. I didn't use any quotient rule. And what I'm about to do now is get the derivative. G prime of x would be, do you see it? It's going to be -3/2. You see how I got that? X to the what? -2 plus 0 if you want, because the derivative of that constant is 0. So I am guessing that the answer they have is going to be -3 divided by, they'll probably make that positive exponent and make it 2x squared. This is what I would get. Is that what they got? Okay. Now, moral of the story? I guess moral of the story is product rules and quotient rules are nice, but if you can simplify first, sometimes you save yourself a lot of work. I'm going to try this 77. Here I go. So 77 says, and again, this is all section 3.3. Come up with a formula for the derivative of f of x times g of x times h of x. Okay. I guess if you're going to use the product rule, we need to have something called u. So I'm going to make u equal to f. And I'm going to make v be g times h. And if I do that, then I know my answer will be u prime v plus u v prime. I know that's my answer. Now, to make things work better, I'm going to stop writing the parentheses with the x in them, kind of like I never do with u and v. So remember, f, g, and h are all functions of x, but just to save time, where it says u prime, instead of writing f prime of x, let's just write f prime. You guys okay with that? And then where it says v, what would I write? gh. Plus, and where it says u, I would write f. But now where it says v prime, I need the derivative of this product, which means I have to use product rule again. That's why they said you have to use the product rule twice. So I'm going to say that doing the product rule on that product, I get g prime h plus gh prime. Right? That's the pattern. U prime v plus uv prime. Because that's the derivative of what v is. V is a product itself. So now, to come up with the formula, the final answer is going to be f prime gh plus, I'll distribute the f here, f g prime h plus f gh prime. And once you understand that, that's really kind of cool. Because now, if I want to find the derivative of a product, I understand how to do it. I take the derivative of each one of the factors separately and just put it with the other functions not taking the derivative. And then I'll add all those pieces together. And see, that's what they want me to do in part B. So I'll try part B next. They say, let's take a look at it. Use the formula to find the derivative of, now it says what? Square root of x times x minus 1 times x plus 3. Could I find that derivative by simplifying first? I could. But it would take a while to simplify that, and you'd have x to the 1/2 power, and you could do it. But I have a feeling this new product rule is going to be nice. So let's see if we can do it this way. So let's go. And I wrote the problem down below. And so again, the idea, if I call these things f, g, and h, okay, what I have to do is take the derivative of f times gh, and then take the derivative of g and multiply by f and h, and then f times g times h prime. That's the idea. Right? That's what I proved in part A. So let's see what we get. All right, I'm going to take the derivative of the square root of x. What's that give me? That's going to be, well, remember, how do you rewrite square root of x? X to the 1/2. So f prime would be 1/2 x to the negative 1/2. Right? That's bing, bing, bong. We haven't learned bong yet. That's Friday. You guys with me? And now I'll write down g, which is x minus 1, and I'll write down h, which is x plus 3, Well, this is 77b. Plus f, that's the square root of x. G prime. Oh, what's g prime? Right, it's just 1, because the derivative of x is 1 and the derivative of -1 is 0. So times 1 times h, that's x plus 3, plus square root of x times x minus 1 times h prime, which is 1. I'm going to bet they simplified a little bit, right? You guys have the answer? This is not it, is it? Okay, let's see if I can simplify a little bit and get the same answer they have. So when I see x to the -1/2, I want to put it in the denominator. So I'm going to write this as, how about I write it this way? X plus 1 times x plus 3 over 2 square root of x.
X minus 1? Yeah.
Oh, x minus 1, thank you. That's a minus. Let's get it right. X minus 1. Not plus, minus. Okay. Plus, let's distribute. I would have x square root of x plus 3 square root of x plus x square root of x minus square root of x. Okay, so now I'll correctly write it as a minus. X minus 1 times x plus 3 over 2 square root of x plus, well, what do you get when you add x square root of x and x square root of x? You get 2x square root of x. And then what about here? I get plus 2 square root of x. Huh. Is that the answer they have? Thanks, guys. Appreciate it. Did I hear? It's not the answer they have. Do they have the answer as one big fraction?
Yes.
Ah, that's very typical. It's nice sometimes to write your answers as one big fraction. And we'll see why in chapter 4. Not yet. All right. Well, if I'm going to write it as one big fraction, I'm going to have to add some fractions together. So I'll put this over 1 and I'll put that over 1, I guess. Is this okay? All right. So we need to add some fractions. So what's the common denominator that I want to get? All right. So let me rewrite this first fraction. If they're going to, I'm going to distribute here. I'm going to get, let's see, x squared plus 2x minus 3. I don't know if they did, but that's not hard. And now here we have, I want to multiply top and bottom by what? By 2 square root of x. Okay, so when I do that, this second fraction becomes something over 2 square root of x. Let's see, I'll have to kind of distribute it. So when I multiply by 2 square root of x times this, I get 4. Square root of x times square root of x is x times the other x is x squared. And then I get 4x. Aha! Now we're getting somewhere. So now the answer I'm getting is 5x squared plus 6x minus 3 over 2 square root of x. Is that the answer they have? Yes? All right, I'm happy then. Yeah, some people said I can't do the algebra at the end to figure out if I have it. Now we have it. Okay. Good. Fun.